So the last time we studied linear regression, and then we studied what was the cost function for linear regression, and we also studied about the gradient descent algorithm. So we were performing the task of regression to predict a value, which is basically a continuous value, and it can take on infinitely many values. But today we'll be talking about logistic regression. The name has regression, but it is not regression, it is a classification algorithm. And we will have a finite set of classes. So for example, let's say you need to classify between two classes. So the task would be called binary classification. Similarly, we have n-array classification where we have n classes. Very simple binary classification problem could be to classify whether it is a dog or a cat, whether you have certain information whether this applicant should be approved alone or not approved alone, whether, let's say, we have certain parameters and the patient is positive or negative in terms of diagnosing a disease. Now for classification, if you remember, the model was a function of x and it had two parameters w and x. We take in a vector x as the input, which is the feature vector. It has certain, let's say it's a row vector of dimension n, and we had m training examples. We had a cost function which was in terms of w and b, and our objective was to minimize the cost function, find w and b such that the model fits the given data the best. We also studied about how to visualize the 3D cost function in 2D using contour plots, and we update the weights and the bias simultaneously. And we also had something called the learning rate, which was a very small value by which, like, how big of a step we are supposed to take. Now let's say we have two features, x1 and x2, and we have certain data points. This could be as simple as taking any two sets of features, any two numerical values, let's say x and y. So let's say when this is x2. So let's say when x2 is this value and x1 is this value, we have this data point, and this is of, let's say, class 0, and the x is class 1. So let's say it could be the number of red blood cells and then the hemoglobin, and then we classify between two classes of a disease. Now in this case, the algorithm we would use would be logistic regression, and you can see that there is some sort of a boundary here between the two data points or the two kinds of data points that we have, and we call this boundary the decision boundary. So essentially, if a data point is to one side of the decision boundary, it is of a particular class. Now if we take a very simple case of a one-dimensional input, so we only have some input, let's say the size of a tumor, and this is the class 0 or 1, wherein we say whether it is malignant or not. So if we try to fit a linear curve here, a linear regression curve, so the line could be something like this. Now you might think malignant is like cancerous, or whether it is a tumor or not, whether a tumor is malignant or cancerous. let's say benign or malignant. Benign is not dangerous and malignant is dangerous. So if I say like I fit this line here, linear regression line, and I have this threshold, let's say 0.5, so you might think that this intersects this here. So you might think that it does a good job of classifying between the two classes. If it is greater than 0.5, the value that this line is taking, then I say my tumor is malignant, otherwise it is not. But let's say if I have an outlier right here, then my curve, the line would be something like this. Now when I find out where 0.5 intersects, it would be somewhere here, and then most of the tumors would be misclassified. So that is why linear regression would not work in such a case. Now, are you aware of the sigmoid function? Yeah. So what is the sigmoid function?
1 for greater than x greater than equal to 0, negative 1 for x less than 0.
Yes. Do you remember the expression also?
1 minus e.
So it is 1 upon 1 plus e to the power minus x. Now when x is 0, this would become 1 upon 1 plus 1, 1 by 2, so it would be 0.5. When x is, let's say, a very large value, then this would become 1 upon 1 plus 0. So it would tend to 1 at infinity, and at 0 it is 0.5, and at minus infinity it is going to tend to 0. So the curve is something like this. So this is the sigmoid function. So the value of y for the sigmoid function would always be between 0 and 1. Now, if we talk about the the linear regression, so we had something like this: f w comma b of x was w dot x plus b. Now this is for linear regression. In case of logistic regression, the function would, okay, let's go step by step. So first I'll call w dot x plus b to be z. Is z a scalar or a vector?
Scalar.
It's a scalar. Now we call f of w comma b of x to be the sigmoid function of z. So this would be 1 upon 1 plus e to the power minus z, where z is w dot x plus b. So this is the function for logistic regression. Now logistic regression would, what would be the range of the output for this function? 0 to 1. So this would essentially give me the probability that my input is of a particular class, of the class, let's say 1. So in this case, f of w comma b of x is the probability that y is equal to 1 given the x vector and the weight w and the bias b. So I hope you remember that this is conditional probability. So this is y equal to 1. What was y? We had two things. One was y hat and one was y. So what is y?
Data true value.
Yes. So y is the ground truth. So what is the probability that this given input belongs to the class 1 given the weight w and the bias b? So, and because this function gives me output in the range 0 to 1, so I know that it would be a probability only. It would not be out of the, like, it would not violate the first axiom of probability that p lies between 0 and 1. Now I mentioned something called the decision boundary here. So in this case, let's say 0.5 is the threshold. So if f of w comma b of x is greater than 0.5, I will make y hat 1, and similarly if it is less than 0.5, y hat would be 0. Now when would the function give me a value greater than 0.5? When this thing would be greater than 0.5. So when 1 upon 1 plus e to the power minus z is greater than 0.5, so z would be, if you look at the graph, this is the graph,
Positive.
z would be positive. Now what was z? Z was w dot x plus b, so w dot x plus b is greater than 0. Now let's say we have the input feature as x1, x2, the case where I mentioned above. So let's say this is the input. So in this case, I said that w dot x plus b should be greater than 0 for y hat to be 1, because in this case my f of w comma b of x would be greater than 0.5. Now if w dot x plus b is greater than 0, it means that w1 x1 plus w2 x2 plus b is greater than 0. Now if I try to make it equal to 0, I get the boundary. Now when it is equal to 0, I would get a straight line. Okay, so if my function has a value, so the function gives me an output in the range of 0 to 1, and this is my probability that y is equal to 1, and I say if it is greater than 0.5, probability is greater than 50% that it belongs to 1, I say that it belongs to 1. Now when will the function have a value greater than 0.5? When z is greater than 0. Z was wx plus b. If I have a two-dimensional input, I would have x1 and x2. X vector would be right. Now, and my w vector would be w1 and w2. Okay, w1 and w2 row vector only, we are taking dot product. So w dot x plus b is greater than 0, so w1 x1 plus w2 x2 is plus b is greater than 0. Now if I have w1 x1 plus w2 x2 plus b equal to 0, this is my decision boundary, and in this case this is the line, the yellow line which I have drawn. So the equation of this line is w1 x1 plus w2 x2 plus b is equal to 0. And how would we get this w1 and w2 and b? What were we doing the last time? Yes, we had a cost function, and then use gradient descent to find out w and b. In this case also we would have a cost function, and then we would use gradient descent to find x1 and w1, w2 and b, or basically w vector and b vector. Now in that case I had a very simple decision boundary. Now let's say we again have two features x1 and x2, and this time I have these kinds of input feature. This is my data. So what could the decision boundary look like? it would be a circle. So it could be x1 squared plus x2 squared equal to some constant. Now the decision boundary could even be an ellipse or a parabola or anything, so it could even have this kind of an equation, which is a general equation for a conic. Now this, in this case, like when you see these things, these would essentially be your I can call these like capital X1, capital X2, capital X3, capital X4 and capital X5. So you would have to do the feature engineering in such a way that you are able to get the right kind of decision boundary for your data. Now we'll come to this in a little more detail after we first define the loss function and the cost function. Now if you remember, for linear regression, this was the cost function was 1 over 2m. So this was the cost function for linear regression. But in this case, if we have now f of w, this was just w dot x plus b, but now we have 1 over 1 up plus e to the power minus wx plus b. So in this case you will see that this loss function would not be convex. So in that case the loss function was convex, and using gradient descent we were able to converge and find out the global minimum, and we call this function convex. But for logistic regression this cost function would not work out, as it is not convex, and then gradient descent would not be able to converge to a global minimum, it will converge to a local minimum. So in our case, if we have this same cost function, then for the model the loss function could be arbitrarily wavy. So in this case, how do we define the the cost function? Now there are two things. I'll introduce a loss function as well today. What we'll basically do is we take this 2 inside, and I call this to be the loss function, and then the average of the loss function is the cost function. This is the cost function. Our objective is to minimize the cost function. Now the loss function for logistic regression is something like this. So loss function for loss function for a particular I
ऐसे नहीं कर सकते कि लीनियर रिग्रेशन की जो लाइन है उसके परपेंडिकुलर.
Okay, so even in that case, let's say what we have this one. If you do this case, then this might be able to work out for this particular data set. But when you have, let's say, a lot of different features, let's say in this case, what would the perpendicular to the linear regression curve be like? Okay, so in this case, if we're trying to you're essentially trying to just say the decision boundary would be perpendicular to the linear regression thing, but as you already saw that we can have such kind of classes, and in this case we have more complex decision boundaries, and a simple linear regression would not be able to fit in to this kind of cases. So you have complicated curves, and a polynomial regression could work, but again at the end we need the classes, we don't need a value. So you're kind of suggesting the same thing as logistic regression only. So you're suggesting to like fit a polynomial decision boundary, which we're already doing, and then we have a sigmoid function to classify to which to give us the probability that the given input is of a particular class. So this is the loss function. Alright, so what is the graph for log x? It is something like this. Let's say this is f. Basically, loss function in terms of f and y is minus log f for y equal to 1 and minus log 1 minus f for y equal to 0. So this is log of f. Minus log of f would look something like this. And f takes in value only between 0 and 1. So minus log of f would be basically this part. And this was for the case when y was equal to 1. So if y is equal to 1, then we are very close to 0. So the loss function is less. And when when f is close to 0, we have minus log of f close to infinity. So when the actual class is 1, but my function is giving me a 0, the loss function is very high. I am penalizing the function. And the other case was minus log 1 minus f. So let's do log of minus f first. So this is for log of minus f. Then I shifted by 1. So the curve would come somewhere here. Then I invert it. So it becomes something like this. Now my curve is only, my f can take only values between 0 and 1. So this is basically 1. And this is tending to infinity. Now in the case when y was 0 and f is giving me 1, so this is f. Y is 0. Y is 0 means that the ground truth is 0. And f is my predicted label. F is giving me a probability close to 1 that y is equal to 1. So in that case the loss function is taking a value that is tending to infinity. Now this is my loss function. If I just have to write it as a single expression, I can write it something like this.
बहुत अच्छा बनाते हो यार.
Now in this case, if y is equal to 1, then this term would become 0. And when y is equal to 0, this term would become 0 and I would get only this term. So this is basically the same thing. We can just write it as a single expression. Okay. Now what would be the cost function? Times the loss function if w comma b of x for the ith. I keep on forgetting the I for some reason. And y of I. And the loss function inside, we have written the expression as minus y of I times log of. Alright, now if you take its derivative, del j by you will find out that it is actually the same as what we found for linear regression. For linear regression, for the derivative with respect to w, what was the expression? It was something like y hat of I minus y of I times x of I, and we had a division by 2m, and for the jth one also you would have summation from I goes from 1 to m. So this is exactly the same derivative as we found for linear regression, and you can verify that by doing the derivation. And for del j by del b with the derivative with respect to b, it would be the same expression, just xi would not be there, which we did the last time. Now again then we have the same thing, that w would be updated to be w minus alpha times the derivative with respect to w, and this would be for wj, and then we have b minus alpha times del j by del b. Now the mistake that you were doing in your code was that instead of multiplying by the learning rate alpha, you were multiplying by a0 and a1, and a0 and a1 were between 0 and 10, and alpha is generally a very small value, 0.001.
हाँ वो बाद में मैंने किया था, पर उसके बाद
Okay, so I think it would be a good revision if we just go over this code. I think okay, we'll do that in the end if we have time remaining. Now I mentioned that the threshold was 0.5, but is it necessary that the threshold is 0.5, or should we 0.5? The answer is no. The threshold can be anything between 0 and 1, and let's say the threshold is 0.3. Now what could be a case wherein such a threshold could be useful? Now let's say I have a very okay, so if it is 0.3, what could happen? Something which is not positive could also be classified as positive. Now we call this to be a false positive. And when would I not mind a false positive? When it is very, very important for me to not miss out anything. So let's say if I am using this algorithm to classify something for medical diagnosis. Now, if I'm using this to basically ease the process or automate some part of the process or initially just screen off some of the diagnosis. Now, if I get something which is a false positive, the doctor can manually then, like, first I use the algorithm. So first whatever is there, the algorithm, then it gives me some positives and some negatives. I can discard the negatives, and from the positives the doctor manually inspects which are the actual positives. But let's say that it missed out something because of the high threshold, then that would be a negative, and it would be very difficult for the doctor to go through the negatives and to check whether if there is something positive in that, then that would make no sense, that would not reduce any labor. So that is why we wouldn't mind a few false positives in some cases, but missing out those cases would be very expensive, as we cannot manually check the negatives, then that would not at all help us, but we can go through the positives and check if there are any false positives. Now, in my research internship also, the task was to automate the process of software test case generation. Now, the first step in that is to detect causality in software requirements. Now, if we miss out something, then that test case would not be generated. But if we are getting something from the initial classification, the engineer can manually check whether a test case should be generated or not. But if that requirement is missed out completely, then that test case is gone. So in such cases, a lower threshold could also be used, and we wouldn't mind false positives. So this is like to prioritize recall. We would come to recall, precision and F1 in the next class, so I would not define recall properly right now, but I guess you got the intuition. Now let's come to the second part of today's discussion, and that is overfitting. So let's go back to linear regression, and let's say we have a few points. Now if I fit a curve which is something like this, then I say that the curve is underfitting. Underfitting, or it has high bias. On the other hand, if my curve would have been something like this, let's just take the same kind of data points, and if I fit a curve which is something like this, then I say that my curve is overfitting. Or it has high variance. Now, overfitting means basically overfitting to the training data set, and if I give it a new example, it would not be able to generalize well to that one. It is overfitting the training data, and it does not generalize the pattern in the data, and underfitting is that it's not able to capture the pattern in the data. So there could be an appropriate curve would be something like this probably. So what could we do to prevent overfitting? So overfitting is basically overfitting to the training data. And there are three things. One could be we could increase the number of data points so that the curve does not overfit. So the solution to overfitting is increase the data. The second solution is to select a few features, feature selection. and the third one is regularization. Now it could be that you have a lot of features, let's say 10 or 20 features, but you only have a few thousand example training data points. So in that case, increasing the data could help you. And how do we, actually diagnose what to do in case of overfitting or underfitting? We would maybe come to that later, but I could show you an example of overfitting. So in this case, yeah, if you look at the loss function for the training data, you're able to see that it is decreasing. But for validation, okay, we'll come to validation also later on. Let's just say that this is the test data set. You can see that the loss is increasing. So it is overfitting to the training data such that it is not able to generalize on unseen data. And you can see here that accuracy is increasing, so that's just the inverse of loss. Now in this case you can see that for both train and validation the accuracy is increasing and the loss is decreasing. So essentially the model is just fit. It is neither underfitting nor overfitting because it's able to give me good performance in both the seen as well as unseen data. Now what do we do in case of regularization? So this was our cost function for the logistic regression, and we just simply add lambda over 2m so lambda here is our regularization parameter. How do we select lambda? We would come to that later.
Regularization matlab?
Yes, so I haven't yet defined what regularization is. So we have, let's say, two features, x1 and x2, and we would have weights w1 and w2. So let's say this is our model. I'll just write f of x because by now you would understand that f has two parameters w and b, and it is a function of x. So if I introduce, let's say, 1000 w1 and 2000 w2, so this would motivate the algorithm to take a very small w1 because I am multiplying it with a very large value. So I am introducing this 1000 w1 in the cost function. So there would be some loss function. So let's just say that we have the cost function j of w and b. I already have that expression, and to that I am adding this, and I will have to minimize the cost function. So to minimize this, I am adding this 1000 w1. Now w1 will take a value which is very small because I'm multiplying it by 1000 or 10,000 or whatever it is. Now if w1 would be a very small value, in that case it is almost as good as not taking that particular feature. So if I have the model was w1 x1 plus w2 x2. Now if here w1 is, let's say, tending to 0, I am almost ignoring that feature. Now if here I have some small regularization parameter, w1 would take a large value, so I'm giving more importance to that feature. So if I add lambda and wj squared to my cost function, you can prove that it would result in fitting a smoother curve for the data. And this is essentially just to see, you could in feature selection remove some of the features, but if you remove those features completely, then you are losing some of the data. Instead of removing those features, you could use regularization. And how do we like select this lambda and that part we would see the next time. There's a complete cycle of training and then actually diagnosing your model. Like in the first time you would not be able to get a good performance. You would have to like look at various curves, maybe the learning rate curve, to check whether your learning rate is appropriate or not. You could regularize, you could check with cross validation, you could look at the loss curves, to the training loss and the validation loss curves, to find out what is going wrong with the model, whether it is overfitting to the data, underfitting to the data, or whether it is just right. So all of that we would look in more detail the next time, but it would be good to keep this in mind, like just a basic introduction of what overfitting and underfitting is. So in this case you can see that it is just fit, but here it is overfitting to the data. Now, yeah, just to give you more background for logistic regression. Right, so now logistic regression is very useful for explainability. In particular, what I was working on was to develop hand engineered features for a classification problem. Now, if we look at, okay, so these are some features that we have, and we train logistic regression model on these set of features. And how does it help us? The main help here is, you can see that this is the regression coefficient of the logistic regression model on the best selected 28 features. Now we have these coefficients, these are the weights of the model. We can use these weights to interpret certain important properties of maybe whatever your data is. So how do these features help? So the author was able to conclude that basically if I remember the result correctly, using these features, like if you have a positive weight, then you can say that, let's say the text which are have fiction have a very high mass TTR and a high TTR, and these are positively correlated. That higher the TTR, more likely is the text to be fiction. And similarly, if you have a negative value, then it is negatively correlated. And even the numerical value would give us an insight on how important a particular feature is. In contrast to using logistic regression, you have these fancy newer models like BERT, bidirectional encoder representation from transformers. They would give you a much higher accuracy, but those are not easily interpretable. Logistic regression is a very simple function, and you can interpret it easily in terms of the features. What is the importance of which feature and how important is that particular feature? In contrast, these CNNs or BERTs, these are black boxes. You get some input, some output, but you're not able to explain why you got that particular output easily. Like there are ways, there are certain curves like which you could use to sort of explain those models, but not as explainable as these models. So logistic regression is used for explainability. Like this is a thing in research which is like last 2-3 years, quite recent only this paper is. So yeah, logistic regression, even though very simple, is very important, and most of my work was on logistic regression only. And the challenging part is to actually decide the features, like which features should be put into the model, or what are the important features that I should extract from the given data. You would just have some sentences. Now what should be the features that you extract from those sentences, and what kind of model do you use to train on those features, and then how do you interpret those results, and how do you improve the performance of your model, or is there a trade-off between explainability of a model and the performance of a model? So in this case, like in logistic regression, even though we get less accuracy, we're getting higher explainability. If we use those neural networks, we're getting higher performance but lower explainability. So that is kind of a trade-off that depends from a case-to-case basis on what your main objective is. So our objective was explainability and not accuracy, so that is why we used logistic regression on hand-engineered features. So I think that should be enough for today. So do you have any questions?